Hi, Travis. Hi, Wayne. This is John Whitaker for the Probability Graduate Level class, and I believe this is our 27th video lecture. I plan on getting this lecture done, one more, and then another one. So it's 29 video lectures, and that will be our class for the summer. Today, we're going to be talking about the compound random variable and come up with facts about it. And so let us recall what a compound random variable is. So as a definition, what we had was, we said let x of 1, x of 2 be a sequence of identically distributed and independent random variables we let n, big N, be a non-negative integer valued random variable that is independent of the sequence of random variables x1, x2, all the way forever. Then, this will give it a notation, S of n, big N, equaling to the sum. Here we'll say as I runs from 1 to n of x of I, that part right there. It's said to be a compound random variable. And so what we have is that n, S of n, the sub n, we have S of 1, S of 2, all the way forever, for every natural number. But we could make one extension to this definition, and we will. We define S of 0 to be equal to 0, just so that we can talk about that a little later. So that's a recall. What's new is that we'll have a definition in a compound random variable. The distribution of n is called the compounding distribution. Okay. We want to prove a fact now about compound random variables. And it's a very abstract fact. Okay. So here's we'll call it a proposition. And here's what it's named, the compound random variable, I think. Here's what it says. It says, let M be a random variable that is independent of the sequence x of 1, x of 2, whatever, and satisfying the probability that big M is equal to some value n is equal to n times the probability that big N is equal to little n all over the expected value of n for n equaling 1, 2, forever. Then, for any function h of, it's going to be a function of the compound random variable, the expected value, the expected value of S of n, the compound random variable, h of S of n, will be equal to the expected value of n times the expected value of x of 1 times h of S of m. Okay. We want to prove this. Okay, so here's the proof. Well, let's grab what we're looking in the conclusion, looking at in the conclusion, which one side of this equation. The expected value of S of n times h of S of n. Okay, that's equal to, well, writing down what S of n is, by definition, that's equal to the expected value of the sum as I runs from 1 to n of x sub I, so that sum times h of S of n, which we could bring in inside here. So h of S of n, if that's what that is. All right. Now, by conditioning on n, we get that this is equal to the sum as n runs from 0 to infinity of the expected value of the sum as I runs from 1 to n of x sub I, h of S sub n, given n equals to little n times the probability of n equaling to little n. It's expected value of this. And that's what we get by conditioning. That's right, by conditioning on big N. That's what I'm doing. And then that's equal to the sum, as n runs from 0 to infinity, of the expected value of the sum as I, little I runs from 1 to little n, because we know big N is, we're given it's equal to little n, of the x of I such that h, not such that, times h of s of n, so this would be little n, given n is equal to n, times the probability that n is equal to little n. Okay. Now, that's equal to the sum as n runs from 0 to infinity of the expected value of the sum as I runs from 1 to n of x of I, h of s of n. Now, the expected value of that times the probability that n is equal to little n. And the reason that I can drop off this conditionally based on n being equal to little n, it has to do with the independence between n and the x of i's. Okay? I was right there. Yeah, x of I. That's what I'm right. Now, this is equal to the sum as n runs from 0 to infinity. And I can bring this expected value inside. So it's the sum as I runs from 1 to n of x of I, or expected value of x of I, times h of s of n, times the probability that n is equal to n. Okay. Now, don't forget that the x sub i's are independent and identically distributed. So, because x1, x2, forever are independent and identically distributed, and I'll write this other thing, and due to the, I won't go into this, but I'll say the symmetry of h of s of n. Here's what we have. Part of this sum, the expected value of x of I, h of s of n will be equal to the expected value of x of j times h of s of n for all I and j elements of the set of 1, 2, all the way up to little n. All right, how can we see this? This can be seen by comparing the expected value of x of 1, h of s of n, times h of n, to, or and, the expected value of x sub 2, h of s sub n. When the x sub 1s, x sub 2s are all discrete random variables. Okay? As what we can see is the expected value of x sub 1 times h of s sub n. Okay, that's going to be, well, we can think of this as x sub, the sum over x sub 1, x sub 2, sum all the way up to x sub n of x sub 1, h of this sum, times f, the p, so I'm doing this as they are discrete, so that's why I have sums. The joint PMF of x sub 1, x sub 2, all the way up to x sub n, x1, x2, up to xn. And then we're having the independence here. And so we can have this equal to sum over x sub 1, sum over x sub 2, sum over x sub n's of x sub 1, h of x sub 1 plus x sub 2 plus x sub n. Here this will be f of x sub 1 of x sub 1 because of independence times f of x sub 2, x sub 2 times all the way up to f of x sub n sub x sub n. And so here, this is equal to the sum of x sub 2, x sub 1, all the way up to x sub n. This shouldn't be x sub n, this should have been x sub 1. Make that change. So this is x sub n of x sub 1, f of x sub 2 plus, sorry, write down x sub 2, yes, plus x sub 1 plus x sub n. That's where the symmetry is coming into play. And here I'll write down f of x sub 2, x sub 2, f of x sub 1, all the way up to f of x sub n, x sub n. Okay. And this is true as the output values of x sub 1 and x sub 2 are the same. Okay. So we're getting the exact same outputs. And f of x sub 1 and f of x sub 2 are the same. So I'm just switching these, if you will. This line right here is because, so to write everything out, and to talk about the symmetry a little bit. So because the output values of x sub 1 and x sub 2 are the same, f sub x sub 1 of x sub 1 equals to f of x sub 2 of x sub 2, and h of x sub 1 plus x sub 2 plus all the way up to x sub n is the same thing as, that's what I meant by symmetry, of h of x sub 2 plus x sub 1 plus all the way up to x sub n, just rearranging the first ones. Okay, so that's why these two things are the same. And that's equal to the expected value of x sub 2, h of s sub n. So they're the same. So, what we were looking at, the expected value of s sub n times h of s sub n. That's what we're looking at. That's going to be equal to the sum as n runs from 0 to infinity of the sum as I runs from 1 to n of the expected value of x sub I, h of s sub n, times the probability of big N and big little n. That's what we have had. But now we say that's the same thing as the sum as n runs from 0 to infinity of the sum as I runs from 1, well, here I should take this away. What that is equal to is each one of these guys are exactly the same. We're summing them up. How many of them, these right here, are exactly the same? How many of them are there? They're n, so it's n times the expected value of x sub 1, h of s sub n, times the probability that n is equal to n. Okay? Put the h of s sub n in parentheses. This is equal to, now using the relationship we have with that other random variable, m, okay, this is equal to, for the probability n is equal to little n, is going to be equal to the expected value of n times the sum as n runs from 0 to infinity of the expected value of x sub 1 times h of s sub n times the probability that m is equal to little n, where this m is this other random variable that's involved. Okay? Remember, it's that random variable that's independent of the sequence and satisfies that the probability of big M equal to little n is equal to n times the probability of n, probability that n equals to n over expected value. So n times the probability of n equaling to little n all over the expected value n. The expected value n is independent of what we have in the sum. That's equal to the probability of big M equal to little n. So that's the replacement that I'm making. Okay. So that's equal to the expected value of big N times the sum as n runs from 0 to infinity of the expected value of x sub 1 times h of s sub n, given m is equal to little n times the probability that m is equal to little n. And the reason that I can do that has to do with the independence between m and the x of i's. Okay, so this is due to the independence between the m and the x of i's. Okay. And that's equal to the expected value of n. All right, well, we know n, little n is the same thing as big M. So this is the sum as n runs from 0 to infinity of the expected value of x sub 1, h of s. It said little n, but we can put down m now because little n is m. Times the probability m is equal to little n given m is equal to little n times the probability m is equal to little n. This sum right here is nothing more than the expected value of x of 1 h s of m. And that's what we're going to prove. Here's the result. Well, we want a corollary, so from this result, we're going to have another result. I think I can state it. I'm going to state it here. So corollary. Here's what it says. It says, let S of n be a compound random variable and suppose x of 1, x of 2, and so forth are positive integer value random variables. Okay. Now, we're also going to do some notation here. We're going to suppose that alpha sub j is equal to the probability that x sub 1 equals to j, where j is greater than 0. And we're going to have m is a random variable. We ran out of room. So m is going to have the properties found in that compound random variable identity. So m is a random variable that is independent of x1, x2, and so forth, with the probability that m is equal to little n is equal to n times the probability that big N is equal to little n over the expected value of n, as we had before. Then, the probability that S sub n is equal to 0 equals to the probability that n equals to 0, and the probability that S of n is equal to k is equal to 1 over k times the expected value of n times the sum as j runs from 1 to k of j alpha sub j times the probability that S of m minus 1 is equal to k minus j. And that's true for k being greater than 0. We want to prove this. So for proof, for k being fixed, we're going to let, so that we can use that compound variable identity, we're going to let h of x be defined to be equal to 1 if x is equal to k and 0 otherwise. And then if we know that S sub n, H times S sub n, that part is going to be equal to, it's going to be equal to K if S sub n equals to K and 0 otherwise. And that's easy to see because it's based on what this thing is. So if S sub n is equal to K, H of it's equal to 1, and that's K, K times 1 is K. And if S sub n is not equal to K, then H of S sub n is 0. 0 times something is 0. All right. Therefore, the expected value of S sub n, of H of S sub n, that's equal to K times the probability that S sub n is equal to K. So, this is going to be a discrete random variable. The expected value is going to be the sum of all of its output values that you can have, but the output values are all going to be 0. Not all output, but we're going to get 0 for this, except when S sub n is equal to K. Okay? So it's K times the probability of this. So remember, the expected value is all the output values of this times the probability of that output value. That's what we have. All right. Now, by the compound random variable identity, okay, here's what we have. The expected value of S sub n times H of S sub n, we just proved this, is equal to the expected value of n times the expected value of X sub 1 times H of S sub little n. So little m, I'm sorry. Little m. Okay, that's what we have. Where we're talking about the m that's involved in the statement. It's corollary, but it matches the m in the compound random variable identity. Okay. So we have that from those two lines previously, K times the probability that S of n equals to K, that's equal to the expected value of n times the expected value of X of 1 times H of S of n, m. Now, we're going to compute that expected value of X sub 1 times H of S sub m by conditioning on X sub 1. Because we know something about X sub 1. So this is equal to the expected value of n times, here this would be a sum, as j runs from 1 to infinity, of the expected values of X sub 1 H of S sub m given X sub 1 equals to j times the probability that X sub 1 equals to j. That's what the expected value of this multiplication is equal to, right there, that sum. That's equal to the expected value of n. Okay. Now, I can replace the probability that x of 1 is equal to j by alpha sub j, our notation. So this is sum as j runs from 1 to infinity of the expected value of x of 1 h of s of m, given that x of 1 is equal to j, times alpha sub j. Okay. All right, well, given that x of 1 is equal to j, I can replace x of 1 with j. So that's the expected value of n times the sum as j runs from 1 to infinity of the expected value of j times h of s sub m given x of 1 is equal to j times alpha sub j. One more line here. This is the expected value of n times the sum, and this j is a constant, can be brought out. You could see that maybe even if you didn't do this at this point, you could do it at the next step. But this is j times the expected value of h of s of m given x of 1 equals to j times alpha sub j. Now what I'm going to do is rewrite that conditional expectation that's behind the sum. So that's equal to the expected value of n times the sum as j runs from 1 to infinity of j times the sum. Okay? So this will be over all the s sub m values. I'm going to call them s sub m prime values of h of s sub m prime. So these are output values times the conditional PMF. Up here it will be s sub m given x of 1 of s, little s of m prime, given little j, and then times alpha sub j. That's what we have. This is equal to the expected value of n times the sum as j runs from 1 to infinity of j. Okay. Now, let's remember about this h output values. These output values are, h of something is always 0 unless the something was equal to k, or fixed k, bigger than 0. So here, that was an integer. So here, we're going to have, in that case it's 1, so it's going to be f of s sub m given x of 1 of k given j, alpha sub j. And again, I had said this, but it's h of s sub m prime, okay, that's equal to 0, except when s of m prime equals to k. That's equal to, well, let me stop there for a second. One more. The expected value then times the sum as j runs from 1 to infinity of j. What is this? This is the probability that s of m equals to k given x of 1 equals to j times alpha sub j. And now let's work on computing this. Now, the probability that s of m equals to k given that x of 1 equals to j, that's equal to the probability that this sum, as I runs from 1 to m of x of I equals to k given that x of 1 equals to j. Okay, so x of 1 is involved in this sum. Okay. All right. That's equal to the probability that we have j plus the sum. So we just put ourselves in that position. So I'm using conditional probability here, where I'm going to put myself in the position that x of 1 was equal to j. So x of 1 was j plus, here it's I running from 2 to m of x of I is equal to k. That's equal to the probability of j plus, we relabel these, this would be the sum, let's say, as L runs from 1 to m of x sub L, sum of those equals to k. Okay? And that has to do a little bit with the independence and identically distributed part. That's equal to the probability that the sum, as L runs from 1 to, oh, this shouldn't have been m, it should be m minus 1. M minus 1 is equal to, x of L, is equal to k minus j. Okay. So, that's equal to, let me write right here, the probability, this is nothing more than S of m minus 1 is equal to k minus j. So, k times the probability that S of n equals to k, so looking back at what we were working with, S is equal to the expected value of n times the sum as j runs from 1 to infinity of j times the probability that S of m equals to k given x of 1 equals to j times alpha sub j. That's what we had earlier. And now, inserting work we've already done. In this proof from here. That's equal to the expected value of n times the sum as j runs from 1 to infinity of j times the probability that S sub m minus 1 equals to k minus j times alpha sub j. Based on what we just found. Okay? Now, one thing to note is when j exceeds k, then the probability that S of m minus 1 equals to k minus j equals to 0. Okay, it's easy to see. Look, the S of whatever's, okay, that's the compound random variable that we're getting here. Remember, it consists of the sum of the x of i's, and the x of i's are all positive. So if j is bigger than k, this is a negative number, that can never happen. So here, what we have is that k times the probability of S sub m equal to k, that's equal to the expected value of n. Here, this sum, no use running to infinity. It's the sum that j runs from 1 to k. times j of the probability of s of m minus 1 equal to k minus j times alpha of j. So the probability that s sub m equals to k, write down what we had it written down. So hold just a second. I'm using the right notation. Yeah, I've been writing n here on occasion, m, but I should have written n. It should have been n, so I made a mistake. I make that correction. This is 1 over k times the expected value then, times the sum as j runs from 1 to k of j times alpha sub j times the probability s of m minus 1 is equal to k minus j. So that's something that we want to prove in this theorem, but it's not all, or in this corollary. Give me just 1 second. Okay, so we've proven part of what we wanted to show, and now we need to show that the probability of s of n equal to 0 equals to the probability n equals to 0. So let's look at that. So now, I'll say this. By definition, the probability that s sub n equals to 0, and this is, I should say, for n being greater than or equal to 1, that's equal to the probability that the sum as I runs from 1 to n of x sub I, if that's equal to 0. Okay? And that's equal to 0. Okay? And the reason that that's equal to 0 is because, remember, the x sub i's are always positive. So the chance that you add up some of them and get that equal to 0 is impossible. Now, note, s of 0 by definition is equal to 0. So the probability that s of n equals to 0 is equal to the probability that n equals to 0. That's what that is. Because n equaling to 0 is s of 0, so the probability of s of 0. That's the only time that you're going to get s of, the only time that you're going to get s of n to be equal to 0 is when n was equal to 0. So that's why it's the same. And that concludes this proof. Okay, I would like to give a fact, small fact, and then we'll call it quits for today. We'll prove this fact. We'll let n be a Poisson random variable with mean lambda. Of course, it's Poisson. It's got to have a mean lambda. We're going to let m, that's our standard notation, be a random variable such that the probability that m is equal to n, this is the standard characteristic m has to do to have that compound random variable identity. So m is equal to n is equal to n times the probability that big N is equal to n all over the expected value of n. That's what we have. This is for n equaling 1, 2, forever. Then what we'll say is that m minus 1 is Poisson with mean lambda. Okay, so that's we're going to prove this. Okay. So note the probability that m minus 1 is equal to n, some number n. All right, so here we want to show it's Poisson, so it needs to have the right PMF, this random variable does. So we look at m minus 1 equal to n. Well, that's the same thing as the probability that m is equal to n plus 1. Now, m, we know, is a random variable that has that relationship with n. And so that's equal to n plus 1 times the probability that big N is equal to little n plus 1 over the expected value of big N. Okay. That's n plus 1 here we're going to have, now n was Poisson with parameter lambda. So this is e to the minus lambda, that's PMF, that's what I'm writing. Lambda to the n plus 1, okay, all over n plus 1 factorial, and then the expected value of n, since n is Poisson, is lambda. This has cancellations. We're left with n plus 1 cancels out with one of the factors of n plus 1. Here, I can write right here. So e to the minus lambda, this lambda, and the lambda to n plus 1 has cancellation, give me lambda to n, all over n factorial. So that tells us m minus 1 is Poisson with mean lambda, and that's what we want to prove. Okay. Gentlemen, that's enough for today. I thank you very much for your time and patience.